A cluster of thunderstorms over the Coral Sea can look messy at first, but under the right conditions, it may become one of Queensland's most important weather threats. Cyclone formation is not magic, and it is not caused by one switch being flicked. It is a chain of ocean and atmosphere processes lining up at the same time. The first ingredient is warm ocean water. In the tropics, warm seas increase evaporation, loading the lower atmosphere with moisture. When that moist air rises into thunderstorms, water vapor condenses into cloud and rain, releasing heat. That heat helps lower pressure near the surface and encourages more air to flow inward. Think of the ocean as the fuel tank, and the thunderstorms as the engine trying to organize that fuel into a rotating system. But warm water alone is not enough. A cyclone usually needs a starting disturbance, such as a tropical low, a tropical wave, or an area of disturbed weather near the monsoonal trough. The monsoonal trough is important because it is a broad zone where winds can converge, air can rise, and showers can gather into larger storm clusters. If those storms keep firing near the same area, the disturbance may start to develop a shared low-pressure center. Next comes spin. Because Earth rotates, moving air is gently turned by the Coriolis effect. Near the equator, this turning is weak, which is why cyclone development is less favored right on the equator. The Coral Sea is far enough away for that planetary spin to help a developing vortex organize, while still being warm and humid enough for deep tropical storms. Forecasters also watch vertical wind shear. Wind shear means winds changing speed or direction with height. Strong shear can push the top of the storm away from the low-level center, leaving the system tilted and disorganized. Weak shear lets thunderstorms stay stacked closer over the center, which gives the circulation a better chance to tighten. Outflow high above the storm matters as well. Air rising in thunderstorms needs somewhere to go, so efficient outflow aloft can help the system breathe. If that exhaust is blocked, intensification may be limited, even when the ocean below is warm. As a system improves, forecasters look for a closed, low-level circulation, persistent deep convection, and storm bands wrapping closer to the core. Satellite images may show colder cloud tops near the center, which often means stronger thunderstorms. Surface observations, scatterometer winds, aircraft where available, and computer models all help agencies assess what is happening. A tropical low is not automatically a tropical cyclone. It may stay broad and weak, especially if dry air intrudes, shear increases, or the circulation never properly closes. But if the center becomes more defined and sustained, winds reach the relevant warning threshold. Agencies may classify it as a tropical cyclone under their framework. For Queensland communities, the key message is to watch the environment, not just one dramatic satellite picture. A ragged low over favourable warm water can improve quickly, while a scary-looking cloud mass can fall apart if shear and dry air take over. Coral Sea cyclone formation is about ingredients lining up: ocean heat, moisture, a disturbance, rotation, low wind shear, and good upper-level outflow. When several of those come together, a tropical low has a better chance of becoming a cyclone, and that is when staying close to official forecasts really matters.